Good. I assume it started now. Hello everyone, welcome to this week's seminar class. We have two talks on NAND flash devices. Bendik is the first speaker and he's going to talk about HeatWatch. He's a third year undergrad student and he's interested in topics of computer graphics and machine learning, right? And obviously NAND flash as well.
Exactly. So, hello and welcome to my presentation on the paper HeatWatch, Improving 3D NAND Flash Memory Device Reliability by Exploiting Self-Recovery and Temperature Awareness. The paper was originally presented in 2018 at the International Symposium on High-Performance Computer Architecture by researchers from Carnegie Mellon University, ETH Zurich, the Safari Research Group, and industry support from Seagate and SK Hynix. So I will guide you through this paper today. Yeah. So, short executive summary of the paper's motivation and its goals. So 3D NAND is prone to retention errors. Self-recovery and temperature effect are two effects that have previously been researched on 2D NAND flash, and the goal of this paper is to extend that research to 3D NAND. So we characterize 3D NAND memory reliability considering those two effects. The paper proposes a unified self-recovery and temperature model, the URT model, that models retention loss, the wear out of the flash cells, self-recovery and temperature effects, and predicts a flash cell voltage that a flash cell holds after a certain time. HeatWatch is a mechanism proposed by the paper that builds upon this URT model to predict the read reference voltage that reduces the retention bit error rate and improves the flash lifetime by 3.85x. So, wrong direction. First, on the background, how flash memory fundamentally works. So, in NAND flash, we trap electrons in a cell to store it. Then we have a picture of a planar 2D NAND flash cell. You can see the blue part is the conductor. This is where we trap the electrons in. And to read our flash cell, we can compare this the trapped electrons to ground, measure that voltage, and compare it to our read reference voltage. So our flash cell is in either state, either if the measured voltage is above our reference voltage or below that reference voltage. We can program and erase our cell by setting the threshold voltage. Setting the threshold voltage has an issue. So we have something called programming variation. That means instead of being able to set a specific voltage exactly, the best thing we can do is set the voltage and we get a distribution what the actual voltage at that point in the cell might be. So we need some margin between our two states that we can have our read reference voltage in the middle to differentiate between them when we read them, because we can't exactly set them to a precise value. Exactly. This write operation is called a program erase cycle or a short P cycle. Exactly. Limitations of NAND flash. So cells wear out when you write to them. That means they degrade over time, and that reduces the cell's ability to hold charge, which leads to retention loss. That means the cell decharges over time. So our initial distribution shifts to the left. As you can see here, it not only shifts, but it also widens, because it might not lose as much charge, but it also might lose a lot of charge. And there's a critical issue with that, because you can see in this, some part of this red curve, of the shifted curve, is now below our reference voltage. So when we read, there's the possibility that we are unlucky and our threshold voltage that we measure is the lowest it can be in this distribution. And therefore, under the read reference voltage, that means our zero we initially wrote into that will be read as a 1. We call that a retention bit error. And we can measure it using as a retention bit error rate. Actually, in this paper, all those limitations are characterized using this rate, because this is an easy thing we can measure and quantify the issues. Known effects in 2D NAND flash. So previously, self-recovery has been previously researched in 2D NAND flash, and it's the effect that a long dwell time, so dwell time is the time between 2 consecutive PE cycles, leads to a lower retention bit error rate. Actually, the paper also discovered that we only need 10% of our cycles to be recovery cycles, so cycles with an extended dwell time afterwards, to yield most of the benefits. Another effect previously known on 2D NAND flash is the temperature effect. So how NAND interacts with temperature. This has been researched in 2010, and we know that with lower temperature during dwell time, we get an increased retention. So a lower bit error rate. When we increase the temperature during programming, we actually also get less programming variation errors. So during programming, so while writing into the cell, it's actually beneficial to have a higher temperature. Well, on the other side, while the cell is idling, so holding the charge, it's better to have a low temperature, because temperature makes the electrons more versatile and more likely to move. Settings. NAND flash density. We can actually store multiple bits per cell by having more than one state and more than just 2 states in our cell. So if we have 4 states, we can binary encode them to store 2 bits in a single cell. That has a few issues though. Because we have less space, so a smaller voltage spectrum per state, there's a higher chance that due to retention loss, we can't identify the exact state anymore. And that increases capacity without needing any additional hardware. But on the downside, it has worse retention and therefore higher bit error rate, and it reduces lifetime, because we have to write if you only want to change one bit, we have to change and access the cell anyway. There's another way to increase capacity. That's 3D NAND. 3D NAND has been developed in 2012 for the first time by Samsung. And the idea is that instead of having one layer of NAND cells, we put multiple layers of NAND cells on top of each other. This requires a drastic redesign of our NAND cell. As you can see over there, there's our original 2D NAND cell and now a redesigned 3D NAND cell. But because we have multiple layers, we can increase the individual size of each cell while still having a higher density. And that means we have a larger voltage spectrum overall. So we can have larger margins between our different states and therefore actually improve our retention bit error rate. And the whole flash is more reliable. So now, 3D NAND cells have a vastly different cell design. And we suddenly started layering NAND cells. So do the self-recovery and the temperature effects still apply that were originally discovered on 2D planar NAND? this is also part of the motivation of this paper, why we move on to that chapter. So, as I already said, 3D NAND was originally first developed by Samsung in 2012. And this paper has the goal of exploring the effects of self-recovery and temperature effect on 3D NAND flash. So we want to create a model where we have both of those effects unified to model those parameters. And we want to leverage that model to leverage the effects to increase lifespan and decrease our retention bit error rate. This is where we come to the methodology. So the use 3D NAND in the paper is multiple chips of the same model to ensure consistency, and all from one major vendor that wanted to stay anonymous. The 3D NAND has stored 30 to 40 NAND cell layers, which is not exactly disclosed in the paper to protect the identity of the anonymous vendor. And we have we store 2 bits per cell, so 4 states. That's called MLC, which stands for multiple bits per cell. So, yes, to measure our retention bit error rate, we have a remote server that communicates with our SSD controller and directly communicates to the SSD's firmware using remote procedure calls over a SATA connection. It can monitor the retention bit error rate, and it can set a read reference voltage. Additionally, there's a heat chamber around the SSD that we can control and measure heat accurately. Characterization. So we want to characterize the self-recovery on 3D NAND and the temperature effect on 3D NAND. So we start with the self-recovery. The idea is to measure the retention bit error rate after a certain retention time, but 4 different dwell times. So again, dwell time is the time between the flash cell rests between different write operations, so between different PE cycles. The setup for that is actually Mielke in his 2006 paper on the original self-recovery effect on 2D NAND discovered that only 10% of recovery cycles are enough to yield most of the benefits and advantages of having an extended dwell times. A recovery cycle is a cycle with an extended dwell time afterwards. So to wear down the cells a little, we first execute 3,000 random PE cycles on the flash with a dwell time of each 0.5 seconds. And then the last 300 PE cycles, so 10%, are recovery cycles with respective different dwell times is what we test. So we test different dwell times. And then we observe the retention bit error rate after a certain retention time and plot this. So these are our results. We have on the x-axis the retention time on a logarithmic scale, and on the y-axis our retention bit error rate, also on a logarithmic scale. And what we can clearly see is that an extended dwell time yields a far lower error rate in the long run. Actually, already after 10 seconds, while in the first 10 seconds, the program variation errors dominate. So our initial temperature while programming, so our initial voltage while programming, and because we did this experiment with a consistent temperature, we can't see any major differences here. While on the other side, in the long run, the retention errors definitely dominate the program variation errors, and you can see that an extended dwell time is definitely beneficial. So the conclusion is longer dwell time, so the time between the PE cycles, yields a lower bit retention error rate. Yeah. So additional discovery made by the paper is that it's most effective to have 3 to 20 consecutive recovery cycles after each other, and more than 20 recovery cycles don't yield any major additional benefits. So for the temperature effect, the idea is to measure the retention bit error rate after a certain retention time, for this time for different temperatures. So first, we again wear down our cell, this time with 10,000 PE cycles, each with 0.5 seconds of dwell time. And then we perform 20 final PE cycles at our target temperature. So we test for different temperatures. All of them also for consistency with 0.5 seconds dwell time. Then we observe how the retention bit error rate behaves after a certain retention time. So this always happen to scroll back. So here are our results. Again, on our x-axis, the retention time on the logarithmic scale, and on our y-axis, again, our bit error rate, also on the logarithmic scale. So the temperature effect. We can see that actually, so lower is better. Higher temperatures perform better in the short term. So while we're programming, which actually matches with the observations made on 2D NAND in 2010. So our variation while programming is most likely lower. And after a longer time, so after a few hundred seconds in this case, the retention loss dominates again, and the retention loss is accelerated by high temperatures. So there it's largely beneficial to have lower temperatures instead of higher temperatures, and we can actually see how the 70 degrees are far worse than any other temperature here. So higher temperature during programming, fewer program variation errors, and lower temperature during dwell time is slower retention loss. So now we can rearrange this plot to actually get the rate of change of our retention, so to get our retention loss speed instead of the error rate. This time plotted against the temperature. Because if we do that, we actually, by applying the least squares method on this, we can see that this matches almost perfectly Arrhenius law, which is a chemical law that describes reaction speeds, which is not that big of a surprise because actually the loss of charge out of our cell is a reaction that this formula was created to model. And we can use this in our mathematical model later. The acceleration factor describes the retention loss speed. So in this formula, and T room is the room temperature, while T real is our NAND temperature. So the URT model, or unified retention and temperature model. We have the initial issue that we have our read voltage there, and our charge might be below it. So if we set a 0, it might be that our threshold voltage is below our read voltage, and therefore we get a bit error. But we can't easily change our threshold voltage. So what we can do instead is adjust our read voltage to, in this case, this would be the ideal read voltage, so we can try to predict our read voltage to minimize our retention bit error rate. The ideal read voltage is between our shifted distributions, the intersection, because that's the lowest point with the least error rate. So to predict our read reference voltage, we want to minimize our errors, we need our original voltage so we need to model our distribution that we achieved while writing into our cell, and we need to model the voltage shift that happened during the retention time. So to do this, the paper proposes this model. This looks very complex at first, but we will get into all the details. So we have this program variation component that predicts our initial voltage, and the temperature effect and the self-recovery effect. So temperature effect with a high temperature that changes our initial voltage is on this side, and there's the temperature on retention effect on retention, and the self-recovery effect that influence our voltage shift. So we use the temperature effect and wear out and the total PE cycles on that NAND block so far to predict our initial voltage and programming. So the variation we had during programming. To do that, we use this formula. There's a lot of constants that we don't have, like the A, B, C, and D. Those are constants that are specific. So it's just a qualitative model that can be adjusted for specific NAND flash that can be applied on by manufacturers. So those parameters would need to be adjusted to apply this model to a certain type of flash. Then we have the self-recovery, the Arrhenius equation we saw earlier in our characterization. And with that, we can actually use this change rate to get an effective retention time considering temperature, and an effective dwell time also considered for temperature. So looking at our initial results here from the experiment where we considered different dwell times, if we plot them in another way and use these squares, we find out that there's the retention loss rate decreases linearly with a logarithm of dwell time. We can use this in our model to combine all of those factors to yield our delta of voltage that our distribution most likely shifted with. This model also accounts for the wear and also the NAND specifics. So this equation is not just qualitative. Yes, so this is our final model where we, on the one hand, use the temperature effect and the cycles to predict our initial voltage distribution, and then on the other hand, use the temperature to predict an effective dwell time and an effective retention time, and then use our total cycles that we've written to that cell so far to predict the distribution shift. And this model has actually a really good error rate of only 4.9%. So now that we have this pretty accurate model, we want to leverage it to actually increase lifespan and decrease our retention bit error rate on actual flash, ideally without harming performance though. This is where HeatWatch comes in. So HeatWatch is a program that's on our SSD controller in the firmware that sets the read reference voltage by applying the URT. So it predicts the initial voltage, and to do that, we just saw all the things the URT needs to predict the initial voltage. So it first needs to log data. And the data it needs to predict the initial voltage is the SSD temperature at the time of the last P cycle on that cell, so the time of the last write, and the timestamps of the past 20 full drive writes. Additionally, the total PE cycles per flash block. For the modeling of the retention loss, HeatWatch is using the current SSD temperature. The acceleration predicts an acceleration factor based off of that using Arrhenius law, and then uses the timestamps of the past 20 full drive writes to calculate those effective retention loss times and effective dwell times. So it scales the dwell time by the acceleration factor that was logged. And it also considers the total PE cycles written so far to predict the voltage shift. So now we want to compare the HeatWatch model against other models and ideal models that might be in use. So to do that, we need to track the bit retention error rate that we already have in our experimental setup. And the researchers applied 28 commonly used storage traces, which are parts of data, which are chunks of data that will be written on the drive. So it simulates a 7-day workload each of those 28 traces. So for that experiment, we compare 4 different models. One with a fixed read reference voltage. So we just have a fixed read reference voltage and we just let all the retention loss, everything happen and ignore it. A retention only model that doesn't consider the acceleration that happens. So it ignores Arrhenius law. And HeatWatch and Oracle. Oracle is just a non-implementable ideal predictor that does not exist, but serves as a reference. So those are the results. In our first graphic, we have a plot of P cycles. So the cycles written during the workload against our error rate. So lower is better. This is of all storage traces. So after applying all storage traces consecutively, so writing all the data, this is what the graphs look like. So the worst performer is by far the fixed V reference voltage, which is no surprise. The retention only is a little better, while HeatWatch almost matches our ideal oracle, that can't exist. So we actually have a really good model here. On the other hand, over there, we have the names stand for different storage traces. And there you can also see that, again, the fixed voltage is performing very badly. The retention only is kind of doing okay, while HeatWatch is almost matching Oracle's performance. Yes, HeatWatch almost matches Oracle. So now to come to the conclusion of the paper. The paper is a first detailed experimental study on 3-day NAND flash memory reliability considering the self-recovery and temperature effect. So it also shows that inaccuracy of prior models for planar NAND if they would just be applied onto 3D NAND. So we can't do that. And it proposes the URT that considers those two effects and retention loss and wear out to give us a good estimate on the threshold voltage. And then there's the implementation HeatWatch that leverages our URT to actually improve flash lifetime and reliability by setting a read reference voltage considering the URT. Analysis. So strengths of the paper are that there's a lot of collected data, a lot of experimental data that's new, that hasn't been researched in that way before. And that's a lot of data and correlations that further research can build upon. And there's also new findings for 3D NAND self-recovery that were not there before were not found before in 2D self-recovery, like that it's most effective to have 3 to 20 consecutive recovery cycles. Additionally, HeatWatch itself is a huge strength of that paper because it's directly applicable to a real world scenario and applicable by NAND vendors. And it has a very low retention bit error rate and extends lifetime by a lot. So weaknesses of the paper are that only a single vendor was tested. Also, although the authors are pretty sure that, and also ensure the reader in the paper that there wouldn't be any major differences, especially because the NAND specific parameters can also fit into the model. So it's mostly a qualitative model. And then the self-recovery characterization. So we made the assumption in the characterization of the self-recovery that only 10% of recovery cycles are enough to yield most of the benefits, which is true and has been shown by Mielke in 2006 on 2D NAND, but we don't necessarily know that also holds true for 3D NAND, and that's not research in the paper. And 3D and HeatWatch only alters the read reference voltage. While having the entire URT, it could also leverage other effects to even improve further on reliability and lifespan of NAND. For instance, the thing we had one slide earlier, that it's most effective to have 3 to 20 consecutive recovery cycles. We could also alter the scheduling of the write operations to account for that, and therefore yield better results. Discussion. So is there any reason to doubt this assumption that 10% of recovery cycles are enough to yield most of the benefits, which is true on 2D NAND, but does it also hold true on 3D NAND? What is your opinion regarding this? Yes.
Just a guess. Oh, sorry. Just a guess, the temperature might be higher in a 3D stacked NAND, so the potential bit error rate might be higher, so maybe more than 10% of recovery cycles are needed. Yeah.
I actually don't know whether the temperatures are actually.
Yeah, I also don't know.
Yes, I actually don't know whether the temperatures are actually higher in 3D NAND. I don't think they necessarily are, but it might be that due to the different layout, the amount of recovery cycles needed and might change. Maybe we also even just need fewer of them actually, because we have larger cells to begin with. So leveraging the findings on the recovery cycles, do you think that it would be there can a case be made that we need a program that also operates in SSD controllers firmware to leverage the effectiveness of the 3 to 20 consecutive recovery cycles on 3D NAND? So do you think there might be a benefit in doing that? Because the paper has shown that It actually improves reliability, and the SSD controller controls the writes on the it can write to a different cell to spare a certain cell and extend its dwell time to actually make a cell just to schedule the recovery cycles. So we could optimize the PE scheduling, so the program array scheduling on the SSD controller to account for that. Here are my image sources. Most of my images are actually from the paper itself, so the graphics. Some are from TLC, and then thanks to my mentors for supporting me further. I will keep this through. To keep this.
Yes. Is this you?
Yeah.
Oh, thank you.
Oh, website. Okay. Yeah. So you uploaded. Page you uploaded.
What did you do?
Separate.
I think she didn't send it to
The upload to the course
Website?
website.
Okay.
Yeah.
All right, so here.
Scroll the second top. Yeah.
This one.
Seminar.
This one.
Yeah.
Okay.
That's schedule.
Sorry, 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 sorry.
Search your
The
schedule.
terms.
Scroll. Available. Yeah.
In here. Yeah.
Okay. This one.
You can check it.
Is this full?
Yes.
That's one. You need to share the screen.
Yeah. All right. Let's start this.
Yes.
Artists.
It's easier if you just start the presentation first. Or PowerPoint.
It's here, I guess, right?
Yes. First here, here.
Let me introduce our second presenter, Ian. Ian is a first year undergraduate student, and she is very interested in memory and computer architecture. The paper Ian gonna be present is talk about the how to use reprogramming to increase the capacity of 3D TLC at the same time to improve the endurance and performance. Ian, yes.
Yes. Hello, I'm Yang Hong. and I'm an exchange student in UGH, and I also studied in Korea University. Today, I'm talking about the paper about reprogramming 3D TLC flash memory. As the scale of SSD evolved from 2D to 3D, there is the additional challenge such as endurance and access latency. In this paper, they focus on increasing capacity and improving endurance and the performance. And the key idea of this paper is programming the TLC as MLC, and if one of the 2-bit is invalid, the reprogram operation can be carried out. And in this paper, we reprogrammed lower states to the higher states. Here is the outline. And first, I'm talking about the background of this paper. This picture is about the 3D flash memory-based SSD. There is the host interface which connects between SSD and host system. And also there is the flash controller. It contains garbage collection and data allocation and flash translation layer. In the flash controller, there is a garbage collection which secures storage space that is no need for computer program. And also there is data allocation, which is the process of distributing and assigning data to different storage nodes. And there is the flash translation layer with mapping between logical address and the physical address. And also there is a flash chip controller which connects the flash chip and flash chip controller. And also there is the most important part of this flash memory inside the plane. It determines the difference of the 3D SSD and the 2D SSD. And let's look at the block architecture of 3D SSD. Based on the vertical architecture, the layer contains several world lines, and it is lined on the horizontal layer. And each world line consists of multiple flash chips, flash cells, and there is only one data for one cell, and also triple level cell can contain 3 bits in the one cell. This graph is the most important graph in this paper. It is about the voltage distribution of triple level cell. In the x-axis, it means the voltage threshold in the flash cell. And the y-axis, it means the probability of voltage threshold. And in the triple level cell, there is the number of the bits is 3, so therefore there is the 8 states. And in the 3 bits per cell, there is LSB and CSB and MSB. LSB means the least significant bits, which means the bits is located in the lowest place. And MSB is the most significant bits, and the CSB is central significant bits. And in this paper, we think about the TLC as MLC, so therefore we only focus on MSB and LSB. Here's an example of 8 bits. There is the MSB, which represents the value of 128. And also there is the LSB, which represents the value of 1. And the basic idea of this paper is program the TLC as the MLC by using the first 4 voltage case. Therefore, we only focus on MSB and LSB. And the low voltage state can be reprogrammed to the higher voltage state. Also, in the past model, they can be only reprogrammed for the one time, but by using the reprogramming, we can reprogram for the several times before erasing. And in this paper, we can program for the 3 time, and also there is the 2 time of reprogramming. For 2 bits, we can reprogramming, and it is depending on which bit is invalidated first. So therefore, for each bit can be changed for 2 type of value, and also in this table there is the 8 stage change in the reprogramming. And I explained about the reprogramming by using the example of LSB and MSB. For the first reprogramming by using the LSB, there is the 8 states of possible transition in the uphold table. By looking the graph, if we reprogramming by using the LSB, there is the 2 backward transition. Backward transition cannot be updated before erasing, so they will be mapped to the P4 and P5. And therefore, all LSB updates is represented by increasing voltage. And next, we reprogrammed it by using MSB. There is also 8 possible state changing in the lower table. And if we reprogramming by using MSB, there is also 2 backward transition, like 1 0 to 0 0 or 0 1 to 1 1. Therefore, it will be mapped to the P5 and P6. So all update MSB is represented by increasing the voltage. And this picture is all possible value transition, and I'm talking the first example of reprogramming by using twice of LSB. First, in the graph, there is the 4 states in the left side of the graph. And if we reprogram by using the LSB, there is also two backward transition, and like 002, 01, or 102, 11. Therefore, it is mapped to the P4 and P5, and all LSB updates is represented by increasing voltage. And also second reprogramming by using the LSB, there is also 2 backward transition, and we can map the 4 state from P4 to P7, and it will be increasing the voltage. Therefore, triple level cell can be reprogrammed at most twice, and each cell stores 4 bits during an erase cycle. And now I'm explaining the problem of previous work and goal of this paper. As SSD is developed, we want to reduce cost per bit, and we adapted the higher bit density like MSB or TLC or QLC, and also constructing valid architecture like 3D SSD. It can be increased the capacity, but it also reduced endurance or operation speed. Therefore, it is the problem of the previous work. So we think about the reprogramming for 2D NAND SLC SSD by dividing the large voltage range into the small range. But it cannot be applied to the 2D TLC. It is because the state interval of the 2D TLC is too narrow to apply it. So in this paper, we think about the reprogrammable 3D TLC SSD design. The goal of this paper is to improve capacity and also improve endurance and performance. And here's the design of this experiment. First, there is the reprogrammable 3D TLC SSD, and there is the three module like timestamp recording and reprogrammable reprogram reference and fully invalidate. And also, we divide the data for hot data and cold data. Hot data can be reprogrammed and it can be reprogrammed before erasing. And also cold data is for programming. And in this paper also, we divided the hot data for 4 parts by using update time interval. For hot data, there is divided from within 30 minutes and 30 minutes to 60 minutes and 60 minutes to 112 minutes. And also cold data means over 120 minutes. And also cold data cannot be updated. The figure is about the flash block, and we divide the block for normal block and reprogram block. For the normal block, it is for regular programming, and for the reprogram block, it is for reprogramming. First, time in arriving data is programmed as normal block. And the next, hot data is programmed or reprogrammed into the super layer. And finally, reprogrammable super layer is used up. Hot data is programmed or reprogrammed to another super layer. Then we can look the reprogrammable block. I explain how write can be programmed and reprogrammed. There is one physical layer per reprogrammable super layer, and each physical layer contains 4 word lines. And each word line is first reprogrammed for state P0 to P3. In this 2 column, there is 2-bit write in the MLC. And there is A stage arriving. And if we look the word line 0 and word line 2, there is first and 2 pair is written. And if we see the word line 2, we want to write the P3. And if we write the P3 in the word line 2, we have to invalidate the previous data in the word line 1. And if the data is invalidated, we can write new data in the word line 2. And next, there is 3 more write is arriving. Let's see the P6. It is the new write request. So if you want to reprogram in the word line 0, the previous data have to be invalidated. And the data, the P0 is invalidated in the word line 0, so we can reprogramming the P6. And P4 and P1 it can be also programmed by invalidate the previous data. And next, finally, the P8 is reprogrammed in the word line 0. Because the previous data of the P1 is invalidated. So there is the 2 reprogrammable in the word line 0, and it will be the candidate block. And in this paper, for the experiment, we use the SSD-based RAID 5 system. And to match the characteristic of 3D TLC SSD, we use 3 modifications. And there is the result of this paper. The goal of this paper is for improving capacity and endurance and performance. So I checked the results of these 3. For the endurance, we checked the program and erase cycle. There is the page write per erase operation, and it means the number of page writes before erasing. And if the page write is increased, it means the number of erasing is decreased. So therefore, it means the endurance is increased. So in this graph, we can check the page write is increased. So we can check the endurance is also improved. And next, I'll check the results of the performance. We check the read and the write latency, and also both of them are reduced. It is because for read performance, only 2 read writing operations are required. And in the write performance, the garbage collection is reduced, so it is, we can see that it is also reduced. And the result of capacity, in this graph, we can check the percentage of capacity is increased. Therefore, it is because the more data is stored in the word line. For the conclusion, this paper is think about the reprogrammable SSD design, and also check the case for the 3D TLC SSD based RAID 5. And this paper can check the endurance and performance and capacity is improved. And there is the analysis for strengths and weakness. First, I think this paper provides a new solution to the problem occurring by increasing bit per cell. They say the bit per cell come from like 2 to 3, like MLC or TLC, and also analyze the feasibility of the solution at the beginning of this paper to improve the need of this method. And also, it is the new result that has not been done in the past. And for the weakness, I think this paper only focused on the part of positive results. In this paper, we think about the TLC as MLC, and the bit per cell can cell is change from 3 to 2. And therefore, if the reprogramming doesn't work well, it can cause the capacity loss. So I think this paper needs more data or method about solving the problem of capacity loss. And also, it only focuses on the hot data, and there is less explanation of cold data. That can be problem of effective capacity. And for the discussion, first discussion is about why in this paper they focus on the hot write, because they divided the data for hot data and cold data, but in this paper for reprogramming, they only focus on the hot writes. Is there any opinion of this question? Yes.
Maybe because the electromobility is still higher.
Is that also, I think, the good opinion of this question? Is there another opinion of this? I think about this question that the SSD is developed, we want to reduce the capacity loss. And the benefit of increasing capacity occur when the data is invalid before erasing. But the cold data cannot be updated, and also update requests are only selected at hot write request. So in this paper, there is the timestamp recording, and it only defines the hotness of write request. And also there is the next question that in this paper, we think about the TLC as MLC, and the bit per cell can be changed from 3 to 2. And if the reprogramming doesn't work well, there can be the capacity loss. Then how can we solve this problem? Is there opinion for solving this problem? Then, in my opinion, the capacity loss is caused by, we think about the TLC as MLC, and the number of bit per cell can be reduced from 3 bits to the 2 bits. And also, if the hot writes are not predicted correctly, there can be caused the capacity loss. And I think we can use the garbage collection to solve this problem. The garbage collection collects the invalid data and erase them from the flash memory cell. Look at the block X, there is the 3 valid data. By using the garbage collection, we transfer this valid data in the new block Y. And we can change the data in the block X for the invalid data. And next, in the garbage collection, we can change all of them for the free data by erasing. So the garbage collection can solve the problem of this capacity loss. And the last question is, in this paper, we think about the TLC as MLC, and there is also the QLC. So using the solution of this paper, how does this apply to QLC? Like we can think about the QLC as MLC or TLC, and also is there an advantage or disadvantage of thinking like that? Yes.
Maybe we can have the reliability of TLC then, but still always the option of extending our graph capacity. So actually using 4 bits per cell.
Yes, we can, and it means that if we think the QRC as TLC, that we can use 4 bits. Is it right?
I mean, if we use it as TLC, we can only store 3 bits, but we can do that as long till we actually need the capacity.
Yes, thank you. I also think about this problem, and first, I think about the QRC as the TLC. In this graph, there is the 8 states in the left side of the graph, and if we reprogramming by using the LSB, there is 4 backward transition, and therefore all LSB updates is mapping to the P4 to P11. And next, if we reprogrammed it one more time by using the LSB, there is also the 4 backward transition, and we can map it all of the states from P8 to P15. So if we think the QLC as TLC, it can be reprogrammed at most twice. And also it means itself can store 6 bits during an erasing cycle. And also I think about the QLC as the MLC. And there is a lot of type of the reprogramming, but in this presentation, I think about the reprogramming by using LSB. First, we reprogramming by using LSB. There is also two backward transition, and it can be mapped to the P4 and P5. Therefore, all LSB update is mapped by increasing the voltage. And also, we reprogrammed one more time by using the LSB. There is also the 2 backward voltage, so it can be mapped from the P6 and P7. And we can do this for like that. And it means if we think about the QLC as the MLC, it can be reprogrammed at most 6. So therefore, each cell can store the 12 bits during the erase cycle. Now I'm thinking about these 2 types, and it means that if we use the reprogramming, we can store more bits in each cell, like then when we doesn't use the reprogramming. And the number of bit cells that can be stored in the each cell, the programming QLC as MLC is bigger than the programming QLC as TLC. But if we programming like QLC, thinking like a MLC, there is more program and erase cycle. And also its program and erase cycle cause a small amount of physical demands to the individual data cell. So therefore, I think also like programming the QLC by thinking about by using QLC as think like MLC can store more bits, but there is also have the bit error generated by program and erase cycle. So I think this is the point of thinking when we using reprogramming on QRC or on other things. And this is my presentation, and thank you for my mentor, and thank you for listening.
Okay, thanks a lot for the two presenters. I think we discussed interesting papers. Fortunately, the discussion was not that live, but I mean, it could be also because of these two papers. It needs some background information. So I'd like to remind everyone to attend to the feedbacks. So I already also created the feedback event for the two presenters today. So yeah, please attend to that and provide feedback to the presenters. We're going to also release the quiz in 30 minutes, so you can also answer the questions. So thanks a lot, everyone, and see you next week.